In this video, we're going to learn how to compare two population means. So first though, let's just say we want to compare two different populations. Some things that we could compare. Well, there's quite a few options. We could compare their means. We could compare their medians. We could compare their standard deviation, their range, etc. Basically, anything that you can think of to compute for one population, you could compare for two different populations. In this example, we're going to compare them just visually. So box plots tell us center and spread. We'll measure center with the median, and spread we'll measure with the inner quartile range. Basically, it's the length of the box. The inner quartile range is the difference between your first and third quartile, so just the length of the box. We're just kind of doing this visually, just kind of a very rough comparison. So let's compare these data sets. I'm going to go through and label these just A and B, so that we can refer to them easily. So when I look at this first set, A and B, notice the line in the middle, that's your median, and it looks like they both have the same median. So their center is about the same. But it looks like A is a lot longer than B, so A is much more spread out. So A has a bigger spread. Whereas if we look at A and B, it looks like B, it has a much higher center. So B has higher center. But their spread seems to be about the same. So their standard deviation should be about the same, their range should be about the same, they're spread out about the same. B just seems to be shifted up. For this next set, let's see, we have A and B. Looks like A, the center is a lot higher. So A has a higher center. A also seems to be much more spread out. So A is also much more spread out. Let's see, for our next one, A is shifted much more to the right, so A has a higher center. The spread doesn't look like it's exactly the same, but pretty close. Looks like B has a slightly bigger spread though. So we can compare them just visually looking at box plots, and this is often what we'll do for diagnostics. When I say diagnostics, just kind of deciding, oh, like what test should we use? Does it look normal? Just kind of glancing at our data to get an idea. We really like to compare box plots. So a little bit more about why would you want to compare two populations. Perhaps the two populations could be people on experiment A and people on experiment B. So you want to, or experimental treatment B. So you want to compare like two different drugs, or maybe you have an old process that used to do something and a new process and you want to compare them and see which one is better. So we want to compare our two populations to see which treatment or process gives better results. And to do this, we're going to take samples from each population. So for example, we might want to compare the number of chocolate chips in a Western Family and Chips Ahoy cookies. So we could compare the average number of chips in each brand. Since Chips Ahoy is the name brand, we suspect that their cookies should have a higher number of chocolate chips. So what hypotheses might we test? So if we want to compare the averages, we could look at the mean for Chips Ahoy and compare it to the mean for Western Family. We think Chips Ahoy should have more chocolate chips, so we would say the mean for Chips Ahoy is greater than the mean for Western Family. Or in other words, is the population mean number of chocolate chips higher for Chips Ahoy cookies than the population mean for Western Family cookies? Now in a previous class, we took a sample of the number of chocolate chips in Chips Ahoy cookies and the number in Western Family cookies, and here are the results. Okay, so you can see our results here. Looking at these, I mean, it's not exactly normal. but our data doesn't have to be exactly normal to do our test. I would think this would be normal enough for everything we've been doing. Looking at the histogram, it's hard to see which one has a higher average, but looking at the box plots is easier to see that Chips Ahoy has a higher average for our sample. Oh, so based on these samples, yes, it appears that Chips Ahoy has more chocolate chips. But what we have to do is decide, is the difference between the two sample averages so big that we believe there's really a difference in the population averages? So it does seem like there's a difference in the sample averages here, but maybe that was just based on which sample we picked, because we know that every sample we pick gives us different results. And so maybe we just happened to pick a sample that was kind of big for Chips Ahoy and a sample that was kind of small for Western Family. So we want to know, is this difference we see due to population differences or just due to which sample we picked? And that's why we have our actual hypothesis tests. So what causes our difference in sample means? Even if our two populations have the exact same mean, we'd expect to see some small differences in our sample means. That's just due to, again, sampling variability or which sample we pick, because every time we take a sample, we get a different sample mean. So we want to know, is the difference we see in our sample means a small difference just due to sampling variability, or is it a big difference due to starting with different population means? So I have here some different categories you can look at. So in this first category, I have these two graphs. Okay. And everything in this first category is where we probably have equal population means. In the right category, we have probably different population means, and in the middle, it's kind of hard for me to tell visually. So you'll see in this first left side that my graphs seem to have fairly similar centers, but when I get over here, it's pretty obvious that the centers are different. So again, all in this left side, you'll see the centers change a little bit, but it's probably just due to which sample we picked. Okay, it doesn't seem like it's a very big difference. Over on the right, you can tell that they're very different, and that's probably because they had different population means. Okay, so I'm going to show you an Excel simulation. Okay. So in this simulation, right here up in the top left corner, I have the actual population, mean, and standard deviation, and I can set them to anything I want. And then over here, you'll see what I actually get when I get the sample. So for example, I'm going to do two groups that have the same population mean of 15 and a standard deviation of 5. Down here, you'll see a dot. Each dot is a value in our sample. Okay. And you can see the box plots. So looking at these two box plots, it looks like the means, so notice it does a little diamond for the actual average. The means are pretty close to about the same. The box plots don't look exactly the same though, because it's just due to that sampling variability. You'll notice over here that my actual population mean is 15, but I managed to find a sample mean of 13 and 13.99. And our standard deviations are 5, but our sample standard deviations were 5.21 and 5.081. So you're always going to have your sample values be a bit different from your population values. So I could try this again. So I'm going to just refresh it and it'll draw a new sample. Okay, so every time I take a new sample, notice my sample mean change. So watch over here my sample means. Okay. So new sample, I get different sample means. My sample means should stay close to 15, but they're going to be different. So like this time I'm at 14.3 and the other one's 15.7. So now watch the box plots. So every new sample, my sample means change a little bit. Okay. Now I haven't actually taught you how to do this hypothesis test, but down at the bottom I have the difference in means and the p-value. So right now the p-value to compare to see if my groups are different is 0.4. So that would be big, and I would think that my groups are about the same. So big p-values mean my population means are probably the same. Okay, we can keep trying though. Notice I'm getting fairly big p-values. My box plots seem like they're about the same. But every once in a while, oh look, what happened right here. My population means are still the same, okay, but I managed to get one sample mean of 15, but the other one's all the way up to almost 18. And that was so big that I got a small p-value, and I would now say I think the population means are different. But obviously here, the population means are the same. So sometimes we end up making mistakes when we do hypothesis testing, or maybe not so much a mistake, but our data, we get unlucky with our data, and our data gives us something that leads us to the wrong conclusion. So sometimes, even though our population means are the same, our sample means will be so far different, just based on which sample we picked, that we'll reject and think the population means are different. Now, let's go ahead and try something different. Let's do the second population mean of 30. Actually, no, let's do 20. Okay, so now you can see that my population sample means are still close to 15 and 20. But my box plots look like they're a lot different. And notice now I'm usually getting small p-values telling me that my population means were different, which is good because my population means are different. Okay, even now though, you might still sometimes make mistakes and you might end up getting a p-value that makes you think that your data or that your population means are equal. So for example, I just barely refreshed it again and I got a p-value of 0.05. That's bigger than 0.05, so I would fail to reject and I'd say, oh, my population means are the same. But again here, my population means were not the same. So just remember when you're doing hypothesis testing that sometimes we get unlucky with our sample and we get something that makes us make the wrong decision. It's also interesting to note here, my standard deviations were 5. If I was to make these standard deviations smaller, like 1 and 1, now those box plots look even more separate and our p-values get even smaller. Okay. So as your standard deviations get smaller, the differences between your means gets more and more significant. So again, even when our population means are the same, we do get differences in our sample means. And as I point out, we're not always making a correct decision. Sometimes we think the population means are equal when they aren't, and vice versa. So let's refresh our mind on errors. A type 1 error means you get a small p-value and you reject a true null hypothesis. So if we were to use alpha equals 0.5, that means if our population means are the same, we'll get a small p-value that makes us think the population means are different 5% of the time, so 1 in 20 times. A type 2 error means we get a big p-value and we fail to reject a false null hypothesis. There's some things here. So if we have a small difference in population means, we might not have enough power to detect it. We can fix that with bigger sample sizes. So a small difference doesn't necessarily show up in our tests very easily, but if you get bigger sample sizes, even small differences will show up. Okay, and even if you have a big difference in population means, we still occasionally get a sample that makes us think our population means are the same. So let's refresh our memory on what independence means, and specifically independent samples. So two samples would be independent if there's no relationship between the measurements in one sample and the measurements in another sample. So again, the two samples can't affect each other. One big way they need to check for that is the same person can't be in both samples. Okay, that would definitely make it so one sample affects the other. There's some notation we should know if we have two populations. Basically, we just put 1s and 2s on everything. So for population 1, we'd have mu1 for our population mean. We'd have sigma 1 for population standard deviation. N1 for our sample mean, we'd have x bar 1. Sample standard deviation would be S1. So again, all we do is just put 1s and 2s on. In this example, a bank manager has developed a new system to reduce the time customers spend waiting to be served by tellers during peak business hours. We can think of population 1 as the waiting times of our current system. So the first day, the bank uses the current system. The manager randomly selects 100 customers. Notice I write N1 for our first day. And finds the sample mean waiting time is x bar 1 equals 8.79 minutes. And then we can think of population 2 as the waiting times for our new system. So the second day, the bank uses the new system. He randomly selects 80 customers and finds their sample time of 5.14. Now we want to compare our population means, mu1 and mu2. To do this, we can look at the difference between the two means. So we'll look at mu1 minus mu2. But we don't actually know our population means, so we can't just calculate this, so we need to estimate it. And how would you estimate mu1 minus mu2? We would estimate it with the difference in the sample means. So we'll do x bar 1 minus x bar 2. Now remember, with sampling variability, different samples from our first population will give us different values of our first sample mean. And different samples from our second population give us different values of x bar 2. Therefore, based on which samples we pick, we'll get different values of our sample mean differences.